Stepping in for Eugene this morning. Our first speaker is, once again, Spradlin, who's going to continue telling us about Multiloop. Please join me in welcoming the speaker. So I just want to start by picking up where I left off last time and making a few more comments about the kinematic domain for n equals 4. And some of these comments should have been made before some of the talks yesterday afternoon. But remember, I had ended by explaining that you can parameterize the set of complex 4 momenta that are null and subject to total energy momentum conservation in terms of free variables which live in P3, which we call momentum twisters. And I also introduced some notation which you saw in many of the talks, the SL4C invariant inner product. So viewing each of the momentum twisters as a 4-component column vector, you can take the determinant in this way. So you saw a bunch of this last time. Now there's a special property of n equals 4 super Yang-Mills theory, which was also alluded to several times. And that special property is that scattering amplitudes are invariant under a symmetry called dual conformal symmetry, which in terms of these variables acts in the following way. Well, I prefer to call it SL4C. It doesn't really matter because these are projective coordinates anyway, so the overall scaling has to drop out. So amplitudes are invariant under SL4C transformations. So you take Zi goes to M, Zi for all I. And this bracket defined in this way is manifestly invariant under that operation. And all scattering amplitudes in super Yang-Mills theory have the property that they're invariant under the symmetry group and hence can be expressed in terms of these 4 brackets. So that's why you see them all the time. And I think it's important to appreciate that this was an experimentally discovered symmetry, primarily by Drummond, Penn, Korchemsky, and Sokachov, but building on a lot of earlier work, in particular, for example, the 5-loop super Yang-Mills calculation of Dixon et al. So it's an experimentally observed symmetry, but it's something which plays a fundamental role because it very tightly constrains the structure of the theory. So as a consequence of this symmetry, we can identify the kinematic domain for n equals 4 super Yang-Mills theory. So much of the rest of my talk today, to take a step back, much of the rest of my talk today will be about the special kinds of non-trivial transcendental functions that appear when you calculate scattering amplitudes. And often we go talk to mathematicians and we try to interest them in these special functions, and aren't they so great, and they have all these wonderful properties. And of course, the first question a mathematician might want to know the answer to is, all right, what are these functions of? What is the kinematic, what is the domain on which these functions are defined? And thanks to dual conformal symmetry and these momentum twister variables, we can provide a very nice and beautiful answer to that question. So if we assemble all of the momentum twisters that specify a kinematic point into a single 4x n matrix in this way, And then we use the fact that that amplitudes are supposed to be invariant under SL4C transformations, which act from the left in this presentation. Well, it's evident, and once again, we might as well go ahead and call this GL4C, because the overall scaling, these are all homogeneous coordinates. It doesn't matter. Everything will have to appear appropriately so that the projective weight cancels out. Now, if you view these as row vectors, so view this matrix now, but think about it in terms of row vectors instead of column vectors, this is just defining the Grassmannian. If you take a 4 by n matrix, modulo by the left action of GL4C, that's just saying that you're looking at the space of 4 planes in n dimensions. Except for one detail, important detail. The important detail is that in addition to taking the quotient of this type of matrix, which gives you the Grassmannian, above and beyond that, we have to realize that we have to remember that each of these is a projective coordinate. Each of the columns is a homogeneous coordinate on P3. So we further have to mod out by rescaling each individual column by an arbitrary non-zero complex number. So C star refers to modding out by non-zero complex numbers. And here I have to put n minus 1 instead of n. And that again has to do with this fact. If I used the GL4, if I used the freedom to allow an overall rescaling of all my rows already here, I can't now overcount. It would be too much to mod that out by n instead of n minus 1, because I've already accounted for the fact that I'm allowed to do an overall rescaling. If you have any doubt about that, just count the dimension of the space. The dimension of this space is 3n minus 15, which is exactly what you would expect, because you have n points in P3 that has dimension 3n minus the action of dual conformal symmetry, this SL4C. Okay, so this is a space that's known to certain mathematicians who call it the configuration space of n points in P3. So this provides a very definite answer to the question of what space is it that scattering amplitudes in supersymmetric Yang-Mills theory are functions on. And at least some of the nice properties, certainly not all, but at least some of the nice properties of super Yang-Mills theory come from the fact that this space is a very rich mathematical structure. And I'm only going to mention this now as a teaser. I might have time to say more about it later in my talk. This space conven has a structure on what mathematicians call a cluster Poisson variety. And for physicists, the salient feature of what that means is, first of all, that there's a natural Poisson bracket on this space. So the Grassmannian itself is a manifold that has a natural Poisson structure on it, and it descends in a natural way onto this quotient space. So let me give you an example of this Poisson bracket. If we look at n equals 6 as a simple example, okay, in the case n equals 6, this is a manifold of dimension 3. So let me write down let's say I want to put some coordinate chart on this manifold. So I need to define 3 coordinates. And one particular choice, there are several possible choices that are good for various purposes. So notice that each of these cross ratios secondly, they're all constructed to have weight 0 under the rescaling of each of the homogeneous coordinates separately. So each particle index appears in the numerator and denominator the same number of times. So these are well-defined quantities on this quotient space. Okay, there are plenty of other cross ratios you might have written. Why did I choose these three in particular? Well, they have the property that these are log canonical with respect to the Poisson structure on that manifold. So specifically, okay, I'm just claiming this for now. I'm certainly not proving it. You can check it. So why do I even mention this at all? Well, in the past few years, we've discovered in some cases, and we're trying to explore more fully, that apparently the scattering amplitudes of Super-Yang-Mills theory know something about this about this Poisson bracket. Just like dual conformal symmetry, this is something that we've so far been trying to explore experimentally by computing amplitudes or by looking up results in the literature where people have computed amplitudes and try to see if there's any kind of connection between the structure of those amplitudes and this Poisson bracket. It's kind of a mystery why there should be such a deep connection. I may say more about this later, but I just wanted to mention this now because it follows nicely after my definition of the momentum twisters at the end of the last lecture. A cluster variety, when you say something is a cluster Poisson variety, again, if I have time, I'll say more about that. But what that means is that there's a natural set of transformations you can perform on these x variables with the property that they maintain the fact that the Poisson structure here is log canonical. So when I say log canonical, I mean that the Poisson bracket between the logs of any two variables is some integer. In this case, it will always be 0 or plus or minus 1. You could have more complicated cluster algorithms where you get higher. Are there any questions about this material? Because I'm going to now change directions quite a bit and start talking about the structure of polylogarithm functions, and maybe we'll come back to this at the end.
So what is the Poisson bracket?
What is it?
Yeah, you're just defining this to be equal to what?
Well, I've claimed, okay, you could take this as the definition of the Poisson bracket, but what I claim to be true, and it is true, is that there's a very natural Poisson bracket on this Grassmannian, which descends to this quotient, and if you just use the Poisson bracket on that space, you will find that the Poisson bracket of log of this with respect to log of that is 1. So you could take it as a definition, but it actually follows very naturally from the Cartan-Lie action of viewing this as a quotient space.
Sorry. So how do you calculate the Poisson bracket explicitly?
I'm sorry?
How do you calculate the Poisson bracket
Oh,
explicitly?
okay. I don't want to get it. Let me discuss that with you in private. I mean, once again, if you take this as the definition, then you can calculate to any Poisson bracket you want. Because if you have an arbitrary function of f of x1, f of x2, and f of x3, and you want to calculate the Poisson bracket with some other, okay, then you could just use the usual rule. Like that, the chain rule. But if you're asking the question, how do I take these variables and compute that they're 1, 1, and 0 with respect to the natural Poisson structure, I prefer not to do that in the lecture. Okay. All right. So we want to talk about some aspects of computing loop integrals. And we heard a lot one example which explores many of those buzzwords. So let's consider, just for fun, the following integral. Okay, this is a two-parameter integral that depends on two independent variables, and it's supposed to be reminiscent of the kind of integral you often or typically would get in quantum field theory after Feynman parameterizing some loop integral. Okay, but it's just meant to be representative. I just picked it out of the hat to show some nice mathematical techniques. This particular example is finite because I wanted to avoid any unnecessary complications that you run into and have to deal with whenever you have divergent integrals. Notice in particular, a particular feature of this is that the integrand, oh, I'm sorry, I want to call this f. The integrand I, which is 1 over a, 1 over b, 1 over 1 plus ax plus by, is a rational function of the internal, that means a and b variables, and the external data. Okay, so if we were actually obtaining this from some Feynman parameterized loop integral, then x and y would be some quantities involving maybe Mandelstam variables or dot products of certain momenta of the external particles, and a and b would be the parameters you might get after a Feynman parameterization, although I've chosen a slightly unconventional domain of integration from 1 to infinity just to make things really simple. Well, the first thing to ask about this integrand is, what are the leading singularities? And here I've chosen an example I, which has unit leading singularities. We heard this phrase quite a bit yesterday. And what that means is that if you look at the loci, well, roughly speaking, what it means, if you look at the loci in A comma B space, where this thing has a singularity, a point-like singularity, singularity of codimension 2, and you calculate the residues at those singularities, you'll find that they are always plus or minus 1. And we'll see shortly the implications of that fact. All right. So, in order to get a handle on this integral, let's just do the following series of very simple manipulations. Of course, half of you have probably opened up Mathematica and you've already done that integral, but the idea is to try to explore some technology here that's applicable to more complicated cases where you can't just open Mathematica and do this. So let's compute the differential of this function. And here I mean the total differential with respect to all of the external data. And now, oh, you know what? For the moment, let me look at the differential of the integrand. Okay, so for the moment, let's work under the integral sign. And now we use the physicist's favorite trick, which is, if you see this function here, d by dx of 1 over 1 plus ax plus by is equal to a over x times d by dA of the same quantity. Okay, and similarly for d by dy, dy of the same thing is d over y, d by dv of the same thing. So that lets me re-express this in the following way. In this term here, the a from the numerator there is going to cancel the a in the denominator. So I'm going to get dx over x times d by dA, 1 over b, 1 over 1 plus ax plus by. And in the second term, I get essentially the same thing, but with x and y exchanged and with a and b exchanged. Running a little bit out of room here. Okay. Now let's integrate both sides. So now let me change this from a formula for the differential of I to the formula for the differential of f by integrating both sides. It's in this example, it's fine to push the d operator through the integral because my the endpoints of integration don't depend on x and y, so there's no problem. And this is a finite integral, so there's no possible subtlety there. I can just pull this d through the integral with no concern at all. So notice now that in this term, I have a total derivative with respect to a. So when I do the integral, well, I just use the fundamental theorem of calculus. You evaluate that at a equals infinity. There's no contribution from the upper endpoint. You just get a contribution from the lower endpoint with a minus sign. Of course, we still have the b integral. Nothing happened to the b integral in the first term. And here, the a, you evaluated it at the lower endpoint, x equals 1. So I'll just, that's why the a is missing there. And then the second term, well, to save time, the second term is just going to end up giving the same thing with x and y exchanged. You're going to get minus dy over y, integral 1 to infinity dA over a, 1 plus ax plus y. But by changing the integration variable's name from a to b, you see that it's exactly the same term as this, but with y and x exchanged. Okay, so notice a feature here that what we've been able to do is here we have a function that's a double integral of a rational function. Later we're going to see that this is something which we call a weight 2 generalized. Well, in this case it's just a polylogarithm function, but we call this a transcendental function of weight 2. And we see that if we take its differential, we can massage it into a form where it becomes a one-fold integral of a rational function. So its differential will be a linear combination of, will involve a linear combination of functions of weight 1 less. And this will be a general feature. All right, now let's take a look at this integral. Or specifically, the integrand for this integral. This integrand does not have unit singularities, unit leading singularities. Well, if you look at the singularities, I mean, this has it's obvious. This has a pole at b equals 0. The residue at b equals 0 is equal to 1 over 1 plus x. The residue of this integrand at b equals 0 is 1 over 1 plus x. It has another pole at minus 1 plus x over y, coming from the second factor here. And if you calculate the residue at that pole, 1 plus x over y, you find that it's equal to minus 1 over 1 plus x. Of course, the sum of the two residues has to be equal to 0. It falls off sufficiently fast. There's no residue at infinity in this case. Okay, so this is not what we call a unit leading singularity normalized integral. So what I'm going to do is I'm going to rescale this it does have unit leading singularity. So I'm going to pull out a factor of 1 plus x, and then insert into the numerator here a factor of 1 plus x. Okay, so all I did was that and that. So this integrand now has leading singularities plus or minus 1. I'm going to take this thing and write it as d log 1 plus x over x. And this integral, well, okay, we've reached the point where finally we can admit that we know how to do this integral, so let's just do it, and you get the logarithm of 1 plus x plus y over y. So the total differential with the function is this thing plus the same with x exchanged with y. I'll go ahead and write the final answer. I'm not going to use it for another few minutes, but it may be instructive. All right. Okay, so this example is meant to exemplify several interesting features which are general. Well, the experts will realize that there's a huge simplification in this particular integral. But some of the features it exemplifies are general. That often, when we look at a finite parameterized loop integral, it can always be written as a rational function. And in many cases, well, in many of the easiest cases, certainly not in the general case, in many of the simplest cases, these integrals evaluate to a class of functions we call generalized polylogarithms. I'll define that more precisely in a moment. Such functions are characterized by their weight. We call this function weight 2 because it involves the dilogarithm function that has weight 2, the square of the logarithm function that also has weight 2, the pi squared has weight 2. So this is a function of uniform transcendentality 2. Every term in this function has the same transcendentality equal to 2 in this case. So it's a general Folk theorem. Maybe it would be safe to call it a physicist theorem, that whenever you have an integral of this type, if it has the property that it can be written in terms of the class of functions we call generalized polylogarithms, then several nice features emerge. For example, anytime in general, the integral of any such function will be a linear combination of polylogarithm functions, but the overall coefficient will be the leading singularity. So here's an example. Well, to turn that around, to phrase it another way, if you have an integral that's normalized to have unit leading singularities, plus or minus 1, it will evaluate to what we call a pure transcendental function. Something like this with no prefactor. Okay, no rational function as a prefactor. Just a pure transcendental function. Oh, and yeah, I should write here the definitions. The polylogarithm function is defined recursively by these formulas. So more generally, if you have an integral with non-unit leading singularities, it should evaluate to